For things like nanochemistry, where at that really small scale, the shape of the material actually matters. And so maybe on a microscopic level, you have like little starburst shapes, or you have perfect cubes, or you have helices or rods. That shape becomes important because on a nano level, a nano scale, you start seeing interactions between those, basically between surfaces and volumes. I would say that's probably the best example I give would be in nanochemistry. So usually solutions are going to be stable regardless. So if they're stable in like a small volume, like 50 milliliters, they're going to be stable in 500 liters. It doesn't matter. More important is the ratio of one compound to another. So if you have too much salt in the water, the salt not all of it's going to dissolve. But you could have as much 1% salt solution as you want. Does that make sense? So one that we think about is, so some of the tests I do are for viscosity reducers. So we might add, say, 500 parts per million of a chemical and see and try to affect a change in that chemical sample. But sometimes we would heat the sample, for example, and wait an hour or 2 hours, and that volume is important for determining how long we need to wait. So if it's a liter of sample, we need to wait longer for it to reach temperature than if it's only 50 milliliters. So I would say heat transfer would probably be one of the biggest, and just time for the solution to stabilize, to equilibrate.